Good afternoon, everyone. I'm going to present you our effort to replace Fortran with Julia. It will get detailed and technical at some point, but it will be mostly high level. And I hope the content will be useful to you, or at least interesting. So just to present myself, in 2020, I joined the load forecast team at Hydro-Quebec. I have a mathematical background, and I've been working in computing for about 40 years, scientific computing. I'm old enough to have used punch cards, and I had my own Apple II computer at home. So that's how far it goes. So I went through different programming languages, and I'm now working, amongst others, with Fortran and Julia. So I'm no longer a developer, but I code our tools and forecast models among a team of advisors. So enough of me. Let's see what you should expect in this talk. So first, some detail about my employer, and then I will present the context of moving from Fortran to Julia and why they must coexist for some time. And currently, the work is on replacing a solver, and you will see what kind of intricacies we've encountered. So I'll detail some of the functionality of Julia we use. So how can we describe Hydro-Quebec? So I got the lazy way and asked Wikipedia. So Hydro-Quebec is a public utility that manages the generation, transmission, and distribution of electricity in the province of Quebec. For those less familiar with geography, let's look where is the province of Quebec. So it's on the northeastern part of North America. Its area is larger than most European countries, but the population is very low. It's 8.5 million in the last census of 2021. So population is mostly located in the southern part along the St. Lawrence River. And here's some publicity to quickly present the company, here are a few numbers. So to highlight some of the numbers, there's 62 hydroelectric stations. Some are a century old, some were recently completed. The length of the distribution lines circles the Earth 5 times, a little bit more. And the transmission line length is longer than any flying distance between any 2 points on the Earth. So a little publicity for my employer. So our electricity system produces and transports some of the most low carbon electricity in the world, thanks to the Quebec climate and geological conditions. The hydroelectric sector in Quebec is comparable to the wind and solar, and is 40 times less emitting than the thermal sectors. So at Hydro-Quebec, I said, I work in the load forecasting team. And to show you what our challenges are, here's the yearly graph of the hourly average demand. So it varies a lot. The highest peaks are in winter and can sometimes be twice as much as the summer demand. So part of the reason is that the house heating has moved to electrical for decades in Quebec. As for air conditioning, it is only useful in some part of summer and really necessary a small number of days in a year, though those numbers are small, seemingly increasing. You can see that the weather has a great impact, on demand, and just looking at the winter season here, it is an important input to our forecast model. We must take into account the temperature, amongst others. even daily variation are important, though not as spectacular. Here are a few curves. The higher ones are in winter, the lower ones are in summer. So even winter, when it's cold at night and warmer in the afternoon, you can see that the curve doesn't follow just the temperature. So daily human activities have significant impact. Lighting, cooking, water heating, commercial and industrial needs, those are just a sample of the demands. So predecessors in our team started our first Fortran model, forecast model, in 1982. So that dates back more than 40 years. Next chapter, moving to Julia. So our Fortran models are reliable and can still be improved. But resources knowledgeable in Fortran are viewed too sparse by the IT group in the company to ensure maintenance of those models in the future. So since tuning of those models require adequate computing speed, Julia language was selected because it offers compilation, but also is a high-level language and ease of use. So those models are part of the grid operating system. And the forecast pipeline must be reliable. So replacing the models altogether in one block would be risky and would take time before achieving appropriate validation. To illustrate this, we are cautiously adding neural network models, but it is already a few years we're spending on that, and we're about to start using them in production. So great care will be taken to ensure that the Julia version of the Fortran model reproduces the Fortran behavior before using them. Only then will we start improving the Julia version. There is an ongoing project to revamp the forecasting tools. More input, more outputs, and adaptable. One of the incentives being the energy transition, with the advent of electric cars, personal electric production, and home automation, including controlling electric consumption during peak hours. At the moment, it's a flat rate cost for users, for customers, but maybe there's some incentive though, some plans where you have reduction if you lower your consumption during peak hours, which is usually in winter. So the code surrounding the forecast model that fetches the data, assembles the input files, and calls the models, the model programs, is already in Julia. That part, we are already using Julia for that part. But we could not spread the resource tenor for the Fortran to Julia conversion. But we could afford internships to at least replace the portion of the code still in Fortran 77. The rest is in Fortran 90. That part of the code is a library and is one of our solvers for tuning our models, to tune the parameters that fits most the historical data. This library was coded in the 1890s, but it was still the best our team could find in 2004 when it wrote a new model. Because it deals with nonlinear constraints, it stands in a small niche, at least it stood at the time. The intern will compare the Julia version to other recent solver and will improve it in his academic work and will publish the results. But our team needs to make sure it will not disrupt our forecast model tuning And we ask for an equivalent code first. So this solver is called an ENLSIP, which is a least square error optimizer for nonlinear problem under nonlinear constraints. We looked at jump and IP-opt. Using those would require, on our part, extensive rework, since the evaluation functions are still in Fortran. Those Fortran functions calculate the error and the constraint margins, error which are the difference between the actual values based on historical data and the prediction from the model. And the constraints control the parameters to be tuned. For those interested in the solver, there's a lightning talk tomorrow on this topic at 10:50 by Pierre Bory. So if you're interested, Pierre Bory is a doctorate student. I'll redisplay the information of the conference at the end. This current talk will concentrate on the Julia-Fortran interface. So replacing the solver. First, I make no claim that what follows is the state of the art. First, we're still using Julia 1.6 because we have to stick with the LTS version. I saw other examples on the web, but none went as deep as I need. You'll see later, but there are several layers of calls. And this is why I decided to share my findings, and hope it could help others. If by chance you have improvements or suggestions, I'll be glad to read or hear about them. So don't hesitate to contact me, and I'll publish my email at the end. So replacing the solver. The modeling program covers calculating the forecast, tuning the model, and other services. So daily it is used in the system to forecast the next day, the next few days, to make sure that the plans are okay. The main program will be converted later. So this is one of the models. And so there's a solver here to optimize the tuning, for the tuning. So since we are only changing the solver, the ENLSIP, where we want to use the Julia version of ENLSIP in blue here. So we need to call the Julia version of the solver in the Fortran code, where the Fortran solver was called. But the Fortran can't directly call a Julia function. So we need to wrap the function, the Julia library, into a function that can be used by Fortran. But we can't, at least I don't know, how to encapsulate, to bundle that with the subrouting. I just talked with someone today that might be possible, but since I didn't know how to bundle it in the executable, we have to do it at the runtime. So we made the program into a subroutine, and then the subroutine can receive and call the Julia version. So we made the main in Julia that can encapsulate the solver, that can also read the parameters and pass the lot to the modeling subroutine. But you see those red arrows here? There's a little problem, because the Julia version was written with the intent of being published to the Julia community. And the convention for the parameters are different. In Fortran, you need to pass the dimension of your arrays, whereas in Julia, you just pass the arrays. So we need to take the Fortran error function. We wrote we wrapped it into a Julia routine that receives the Julia arguments, deconstruct them, and calls the Fortran routine. And then we need to wrap it so that the Fortran can receive it and pass it to the solver. So we could have modified the Fortran code to cope with the difference of arguments, but it was better, we found it better just to keep it away from the Fortran routine, and that the Fortran subroutine didn't have to cope with the different version. It would just use it, whichever one we passed. And that modeling routine now simply needs to pass the function back to the solver it receives, either the Fortran or the Julia one, depending on what is passed. So it seems to reduce the risk. Instead of changing the parameters in the modeling routine, doing this makes it isolated the problem and also allows a simpler to provide either version, decide which one we want to pass, to compare them to make sure that the Julia version reproduces the Fortran one. Now let's take a step back. Okay, so we started with a main modeling program. We modified it into a subroutine. We wrapped the modeling subroutine in the Julia main. The evaluation functions can be passed together with the solver. Here we pass the Julia version, but we can't choose which set we want, so we could choose also the Fortran set. We also made a main Fortran program calling the new subroutine. This addition allows nice comparison testing, and let's detail the different possible tests. First, we can compare the original main, the original program, to the one with the core of it factored in subroutine to make sure that the refactoring was successful. Then we can compare the Fortran main with the Julia main, same solver, to see if the interface was properly set. And here we compare with the same main, the same routine, we simply compare the different solver, the Fortran and the Julia solver. So all those versions help to isolate where detected problem occurs. Obviously, we only need to use the intermediate one when the original and the final one differs. So this pattern will be useful when we incrementally replace the Fortran by Julia. We actually use those patterns for comparing ENLSIP and Julia, Julia and Fortran version on several academic problems, not only within our specific industrial needs. I'm not claiming inventing those patterns, they are simply sound development steps. So before we dive into the code, is there any question on those steps? So let's go. Replacing the solver, the tools. So before showing code extracts, I'll present the tools I used as the Julia-Fortran interface. First, the ccall function, which can also be a macro, but I recently learned about the macro, so I use the ccall. Ccall allows calling code available in shared libraries. The type of the arguments and the return value must be given to Julia to prepare the call. My example shows the function ccall instead of the macro at ccall. And look here, you provide a return type, then the list of argument types, And then you have the list of arguments, and you have to make sure that they align. Whereas in the macro call, you provide the value and the argument type just after. So it seemed more friendly. Yeah, notice that here, I fetch, well, we'll see it later, but you can simply pass the library and the function name here instead of doing it 2 steps. We'll see it later as well. So, and also, as noted in the quote here, when calling a Fortran function, in C, you often pass values, but at Fortran always take a pointer even for scalars. So we also see an example of that later. So the macro at C function, I said that the Julia cannot be called directly. So that's what C function does. It prepares a C callable function pointer that can be passed to the C or a Fortran program routine, mainly for callback. The function name must be given since it's a macro. Inline definition won't work, at least that I know of. On the Julia side, a function must match the argument. And on the Fortran side, the declaration gives the type of the variables. But there's nothing that match between those two, not even the argument length. So at one point, I gave 5 arguments in one and expected 6 in the other. And I didn't know what was going on, but it didn't work. So maybe messages are improved since, but just a warning that can happen. So if you code on the Fortran side, using ISO C binding provides C types and allows the compiler to generate the library with C calling convention. So here we have C double, C int, the chars. So also providing the name here helps skips. Otherwise, you have to find how the compiler named the library, the function in the library. Okay, so I have to speed up. So replacing the solver, the details. Just an example here of calling C function. And for arrays, I use PTRs. And for scalars, I use ref, so the address is passed. Receiving the function. So on the C side, on the Fortran side, we receive, sorry, I should look here. Okay. So on the C side, we receive the pointer, which we declared, the type pointer, and then we convert that with a CF proc pointer to a pointer of a given signature. And then with the signature, we can call it. Calling the Fortran subroutine, using ccall. So we pass, this is, first we fetch the library, then we get the subroutine, and then we pass the type and the list of arguments. Here we when in this example, to pass the solver function, we need to cast the pointer to the function. And sorry, I'm going to. Here we adapt an evaluation function, right? So we have the Fortran subroutine, which is called, and we receive the Julia arguments, and then we simply provide the length of the arrays. I use pointer here, but it seems not recommended for other cases. In my case, it is this Fortran modeling routine that creates the space, the memory allocation. So there's no concern about garbage collection. But if it's a Julia object, you better let the Julia create the pointers and pass the information. And providing the function, passing the evaluation function is the same as passing the solver. So, yes, and also I said we could choose between the Fortran and the Julia. So I used a simple ternary conditional expression to choose which variables to pick. In conclusion, well, we found that Julia can incrementally replace the Fortran. In our situation, we can minimize the risks by converting smaller piece of code at one time and ensure that the converted code behave the same as the original. Any questions? Okay. I'll repeat the questions.
Before you settled on Julia, did you evaluate other languages like C++? And having made as much progress as you did you have second thoughts? Would you have considered other or are you happy to have
Okay. When I joined the team, the decision was already made. But I joined knowing that decision and was happy to to jump in. So, and I have no regrets. I believe Julia is fine for that. Thank you. So this question first.
When you were converting from Fortran to Julia, you were testing equivalency. Did you test for like exact numerical equality between the two? Or if not, how did you decide what tolerances you expect for different parts of the testing?
Okay, so the question is, how did we compare both, and what about the numerical precision? How close did we get? Okay, so yes, there is some slight differences, but it's an iterative. The solver is an iterative process. So we compare each iteration. At the beginning, we can't see no difference with the length of the precision printed, but after like 10 or 15 or 20 iteration, then there's slight differences, and we found that acceptable. But yes, there are slight differences numerically, but workable. Yes.
How long do you think it's going to take to transition the whole model? And if you had some more effort, maybe more support, do you think it could go faster or non-parallelizable?
It is parallelizable. You see, we're a team of maybe 8 to 10 person, and we have other functions. So there's very little assigned to the Fortran. But we're thinking of internships, so student would be welcome. Just,
with interns, how long do you think it would take to replace a larger portion of the model?
Well, there's two aspects for that. One is all the model equations, which I think would be quite straightforward, because those are equations. But there's another part that all those parameters, because there can be 800, 1,000 parameters. And there's different functions for different physics aspects. And there's different versions for different functions. So they have different length of parameters for each. And there's a system that manages all those differences and takes a list of variable parameters and can compress that into one array to be passed to the solver. And that part would be more tricky to my knowledge. So